Hey everyone, welcome back. Today we're doing something super practical and very rewarding. We're going to build real web applications in Rust. We'll look at two of the most popular, battle-tested frameworks in the Rust ecosystem, Actix-web and Rocket. I'll show you how to stand up simple servers, handle JSON, manage shared state, do routing, handle errors, and even test endpoints. The goal is to give you enough real examples, so you leave this video with code that you can run and iterate on immediately. Alright, fire up your editor and terminal. Let's start with Actix-web, because it's very widely used and extremely fast. Actix-web is an async framework built on top of Actix Actor runtime and uses Tokio internally. It's modular, production-ready, and works great for APIs and microservices. First, create a new project. Open cargo.toml and add these dependencies. We will use Actix-web as the core HTTP framework to handle web requests, running on top of the Tokio crate, which provides the necessary multi-threaded asynchronous runtime and macros for non-blocking execution. Additionally, the inclusion of serde, specifically with the derive feature, and serde JSON enables seamless serialization and deserialization of data. Now in main.rs we'll write a small app that exposes a few endpoints, a root route, a JSON echo, a route with path parameters, and basic shared state. First, we import the essential building blocks for constructing an Actix web server, handling data serialization, serde, and managing thread-safe shared state with Mutex. AppState structure defines the thread-safe, shared state for the application, holding a simple integer counter protected by a mutex to allow safe concurrent modification across multiple requests. We defined a simple myObject struct with serialize and deserialize from serde, so Actix can automatically decode incoming JSON and encode output JSON. Index returns a plain text response. Echo JSON accepts JSON of type myObject and returns it back. Get with perm demonstrates path parameters, and increment counter shows shared mutable state using data.counter.lock. In main, we are initializing an asynchronous HTTP server on port 8080 with dynamic routing. A global AppState containing a thread-safe mutex counter is defined, which is injected into the application using web data, so the count endpoint can safely increment it across concurrent requests. Web data is the Actix way to share application state between handlers. We wrap the state in arc-like semantics automatically using web data, but because in this example we use Mutex, we store an interior mutex of type i32 for the counter. The router is configured with 3 additional endpoints: a basic root path returning a static string, a hello/name route that extracts dynamic path parameters, and an echo route that leverages serde to automatically deserialize incoming JSON into a myObject struct and serialize it back as the response. Run it with cargo run. Now if we hit the root route, it will print hello from Actix-web. The echo route with this JSON data will return the same JSON. Now if we call hello/name route with name Alice, it will return hello Alice. And count route will simply increment the counter. That's a compact API. Actix has many more features: middleware, extractors, request guards, file serving, WebSocket support, and more. Let's say we want to log requests in real production app. We will use logger from Actix-web with envlogger. Add envlogger to cargo.toml, and you'll get request logs automatically. Let me show a snippet. Here we basically added a middleware configuration for the Actix web server. Before the server starts, it initializes the logging system using envlogger, setting the default level to info to display useful messages, including those generated by the server. The application then initializes the thread-safe AppState for shared use across requests, as we have seen earlier. Crucially, the app new builder is enhanced with logger middleware using the wrap function, which automatically logs details about every incoming HTTP request and its corresponding response status, ensuring transparent monitoring of the application's activity when it finally binds to port 8080 and begins running. Now let's look at error handling in Actix-web. Good error handling is essential for web apps. We can create custom error handling system by using the thiserror crate. Add thiserror to your dependencies. Let's look at the example. Here, first we defined a custom enum, myerror, using the thiserror crate. Myerror enum cleanly structures different error types like bad request and not found. The key integration is the implementation of the Actix web response error trait for myerror. This trait requires the error response method, which explicitly maps each custom error variant to a corresponding standard HTTP response. For example, mapping myerror bad request to an HTTP 400 bad request response with a JSON payload, and myerror not found to an HTTP 404 not found response. The application exposes 3 services, a simple root route and 2 dedicated endpoints, error and missing, that intentionally return a result that is either a successful HTTP response or a custom error named myerror, enabling the Actix runtime to automatically catch and process the custom error into the user-defined HTTP responses via the response error implementation. Let's switch gears to Rocket. Rocket has a different design philosophy: ergonomic, macro-heavy, and very expressive. Rocket is async and works with Tokio. It's a great choice if you want developer ergonomics, nice routing macros, request guards, fairings similar to middleware, and an intuitive API. In cargo.toml, add the Rocket crate, with the JSON feature enabled for automatic payload parsing. Now in main.rs, write this code. First, we will load the external library Rocket and, crucially, to make its procedural macros, like get, post, and launch, available globally for the current crate. In this code, we have defined 4 distinct routes. Index, a simple get route returning a static string. Echo, a post route that expects an incoming JSON body. It automatically deserializes this data into myObject and returns it, demonstrating JSON request or response cycles. Hello is a get route demonstrating dynamic path segment routing, where the value provided in the URL is extracted directly into the name, string, function argument. Increment, a post route demonstrating shared state management. It uses the counter struct and receives it via Rocket state of type counterguard. It locks the mutex, increments the inner integer, and returns the new count, ensuring thread safety across concurrent requests. Run with cargo run, and you'll have similar endpoints to our Actix example. Try all URLs and see the behavior. Rocket has powerful features like request guards for auth, fairings, startup and shutdown hooks, and form handling. The developer experience is often a bit smoother due to the macros and tighter integration. Let's highlight some differences and trade-offs between Actix-web and Rocket. Actix-web, extremely fast and flexible. Very modular, you compose middleware, extractors, and services. Great for microservices, high-performance APIs, and streaming results. Slightly more boilerplate for some things, but very explicit. Rocket, highly ergonomic with expressive macros, less boilerplate. Very nice developer experience. Route macros and request guards look beautiful. Fits developers who want quick productivity and neat code. Also production ready. Choose it when ergonomics beat tiny performance delta concerns. Both are async, both can scale, both have healthy ecosystems. Choose the one that fits your team. Now, let's dig deeper into a few advanced topics that appear in real projects. Database integration, authentication, cores, static file serving, and testing. For async DB access, SQLX is an excellent choice. It's async, type-safe, and supports compile-time checked queries. Add SQLX with the runtime feature matching Tokio and your DB. The SQLX features are key. Runtime Tokio Rust TLS specifies the use of the Tokio async runtime, which Actix-web also uses, and enables TLS, transport layer security, support. Postgres selects the PostgreSQL driver, and macros enables the use of SQLX query and SQLX query as macros for compile-time SQL checking. A tiny example with Actix-web plus SQLX, Postgres, looks like this. The main function first initializes the database connection pool, PG pool, using the specified connection string. The server is then set up, and the PG pool is wrapped in web data and added to the application state using appdata function, making the shared, thread-safe connection pool available to all route handlers. The application defines a single route, users, which maps a GET request to the asynchronous user's handler. The user's handler receives the connection pool via dependency injection, which is passed as a web data object holding a PostgreSQL pool. Inside the handler, the SQLX query as function, containing the SQL statement select ID, name from users, defines a SQL query, and the fetchAll method is used to asynchronously execute the query against the pool and retrieve all resulting rows. The query as macro is used to automatically map the resulting columns to a Rust vector containing tuples of a 64-bit integer and a string structure. SQLX's query as macro can check SQL at compile time if you enable the correct feature and provide a database URL during build. That's a huge win, catching SQL errors early. Finally, the fetch data is serialized and returned to the client as an HTTP 200OK response in JSON format. Now let's look at authentication. In Actix-web, authentication is typically handled by extracting user information in a custom extractor, a type implementing from request, or middleware. In main.rs, write this code. The core of the logic lies in the implementation of the fromRequest trait for the custom struct authenticated user. This trait turns authenticated user into a request guard that Actix-web automatically runs whenever a handler function includes authenticated user in its signature, for example, protected route. The fromRequest method handles the authentication logic. It first attempts to retrieve a previously authenticated user instance from the request's extensions, which is a local storage space for data on the request object, allowing prior middleware to potentially handle the authentication. If the user is not found in extensions, it inspects the authorization HTTP header. In this simplified example, it checks if the header starts with bearer myValidToken. If the token is valid, it constructs a new authenticated user instance and optionally inserts it into the request extensions for later access. It then returns OK, user. If the header is missing or the token is invalid, it returns error unauthorized, which automatically translates into an HTTP 401 unauthorized response for the client. The application defines two simple routes, the public index route and the protected route. The protected route's signature specifically requires authenticated user. If the authenticated user extractor successfully validates the token, the handler executes and returns the welcome message. Otherwise, Actix-web short-circuits the request and sends the 401 error defined by the extractor. This pattern ensures no handler code is executed unless a valid token is present. In Rocket, authentication is implemented via a request guard, a type that implements the fromRequest trait, allowing it to validate an identity before the handler function is called. In main.rs, write this code. Similar to Actix-web, the core mechanism for authentication is the custom implementation of the fromRequest trait for the authenticated user struct. This implementation turns authenticated user into a request guard, meaning Rocket's runtime automatically executes the fromRequest function whenever a route handler requires an instance of authenticated user in its signature. The fromRequest method attempts to extract the value of the authorization HTTP header. It then uses strip prefix method to ensure the header starts correctly and to isolate the token string. It uses a simple pattern match to simulate token validation. In a real application, this is where you would decode and verify a JWT using a crate like JSON web token. If the token matches, the method returns outcome, success, providing an instance of authenticated user to the handler. If the token is missing or invalid, it returns outcome, error, with status unauthorized. This immediately halts request processing and sends an HTTP 401 unauthorized response to the client, preventing the route handler from ever executing. The application defines two routes. The public index route, which serves a simple hello message and doesn't require authentication. The protected route, whose signature includes the user, authenticated user, argument. This signature tells Rocket to run the authenticated user request guard first. Only if the guard succeeds will the protected route handler execute and return the personalized welcome message. The launch function registers both routes, defining the complete API. Now let's look at the example of an HTTP server that explicitly handles cross-origin resource sharing, CORS, and serves static files from a local directory. First, add Actix CORS and Actix files to dependencies. Write this code in main.rs. CORS is important for front-end apps. In Actix-web, by using the CORS middleware wrapped around the application via the wrap method, every incoming request will be processed to include the necessary CORS headers, like access control allow origin. The permissive setting is the simplest configuration. It effectively allows any external domain, origin, any HTTP method, GET, POST, etc., and any header to access the server's endpoints. While convenient for development, a permissive setup would typically be replaced with specific configuration in a production environment to enhance security. Next is static files or file uploads. For file uploads, handlers accept multipart and stream to disk using async writes. Streaming prevents large memory spikes. The service method configures the server to handle static assets using the Actix files service. This service sets up a specialized route that intercepts requests starting with the path prefix, static. When a request hits this route, for example, a request /static/test.txt, the service attempts to find the corresponding file within the local directory specified by the second argument /static, relative to where the server is run. The Show Files Listing option is added to allow clients to view a directory listing if they browse to the base/static URL without specifying a file, which is often enabled during development but disabled in production. In summary, the application runs on port 8080, allows all cross-origin requests, serves any files found in the local static folder under the /static URL path, and provides a simple hello message at the root path. Now let's test HTTP endpoints. 4 unit and integration tests. Both frameworks provide helpers, and you can use clients like request to call endpoints in integration tests. Dependencies for this setup are Actix-web, which provides the testing utilities, and Actix-rt, the asynchronous runtime that allows the test function to be executed. Actix has test module that spins up a test server. Actix-rt test. This macro is essential, marking the function test index OK as an asynchronous test. It starts the necessary runtime environment so that async code, like network calls and service initialization, can be run within the test. The test index OK function simulates an HTTP request lifecycle against the application logic. The init service helper creates an isolated test server instance, a service object, based on the application's configuration. This step is crucial because it mimics the full application setup, including routing, but does not bind to a real network port, making the test fast and isolated. Only the specific route being tested is included. The test request builder creates a simulated HTTP GET-REQUEST object aimed at the root URI. The call service function executes the simulated request against the local test server app. The result, an HTTP response, is obtained asynchronously. This final step, assert, performs the functional check. It asserts that the resulting HTTP status code is within the success range, for example, 200 OK, confirming the index route handler executed successfully and returned the expected type of response. Now let's look at a minimal Rocket web server with asynchronous integration test. Rocket supports testing via local asynchronous client for launching an instance and tests. The test index function demonstrates how to perform a functional test using Rocket's built-in testing utilities. The function is marked with Rocket async test, which uses Rocket's testing runtime to execute the asynchronous code. Inside the function, we initialize a local test client by launching the application instance defined in the Rocket function. The client runs the application internally without binding to a real network port, making the test fast and isolated. The tracked method enables tracking resources, which is useful for cleaning up after the test. Then we dispatch the request. The client simulates an HTTP GET request to the root route and obtains an asynchronous response object. Finally, we assert. The final assertion verifies that the HTTP status code returned by the simulated request is exactly 200 OK, confirming that the index handler executed successfully. This pattern tests the entire request response lifecycle from the client's perspective. Let me close with a full minimal example in Actix-web that ties together many of the parts we discussed: state, DB pool, JSON, errors, and logging. Write this code in main.rs and adapt the DB URL and dependencies as needed. It's a solid skeleton for a microservice. Let's break this down. This Rust code implements a small asynchronous REST API using Actix-web and SQLX for database interactions with SQLite. We use .env to load configuration, like database URL, from a .env file and tracing subscriber to initialize logging, which is then utilized by the logger middleware for request tracing. It connects to a SQLite database specified by the environment variable, often configured as an in-memory database, SQLite memory. Upon connection, the application immediately runs a create table if not exists query to ensure the user's table is present. The resulting database connection pool, SQLite pool, is then wrapped in web data and injected into the Actix application state, making it available to all route handlers. For error handling, we defined a custom error type, app error, using the ThisError crate to neatly encapsulate two types of errors, DB for database errors and invalid input. By implementing the response error trait for app error, the application automatically converts these custom errors into standardized HTTP responses. For example, a database error maps to a 500 internal server error response, while an invalid input error maps to a 400 bad request. This ensures that all route handlers can return a consistent result that is either a successful HTTP response or the custom application error, app error, greatly simplifying error management. We set up two primary API endpoints. First is post/users via createUser. This handler accepts a user object. It includes input validation, checking if the name is empty, which, if failed, returns an app error, invalid input. If valid, it executes an insert query using SQLX query with bind parameters to prevent SQL injection, returning the newly created user object with its assigned ID and a 201 created status. Second is get/users via getUsers. This handler fetches all user records via a select query. Since query as can be tricky with in-memory pools, the code uses SQLX query and then manually maps each database row to the user struct before returning the complete list as a JSON array with a 200 OK status. Let's test it. All right, we've got our server up and running, connected to that ephemeral SQLite database. Let's start with a quick smoke test on the root route. First up, a simple get to the root path. This just confirms the server is alive and listening. There it is. We get a clean 200 OK and a friendly welcome message. Now for the main event, creating a user. We're going to send a post request to the user's endpoint. We need to set the header to tell the server we're sending JSON and then pass in our data. Beautiful. We got a 201 created status, and the server responded with the full user object, including the new ID of 1. That confirms our create user handler and the insert query are working perfectly. But what if a bad request comes in? Remember, we added validation to prevent empty names. Let's intentionally send a user with an empty name field. There's our custom error handling in action. We get a crisp 400 bad request status, and the JSON body contains the explicit error message. Name field cannot be empty. This proves our response error implementation for app error. Invalid input is correctly translating application errors into standardized HTTP responses. Finally, let's verify our list endpoint. We'll send a simple GET request to users to see what's in our database. And there is Alice. The GET users handler successfully connected to the SQLite pool, executed the select statement, mapped the rows, and returned the result as a JSON array. Everything looks great. Our Actix-web and SQLX integration is solid. And with that, we've successfully implemented and demonstrated a full API lifecycle, from routing to robust database and error handling. All right, that's a wrap for today. We covered both Actix-web and Rocket, walked through routing, JSON handling, shared state, error handling, DB integration, and testing. Which one would you prefer, Actix or Rocket? Tell me in the comments.